So welcome to our 16th lecture on prosody, and today we'll be talking about normalization. So why are we concerned with normalization? We'll be looking at normalization of the types of frame-based features that we saw in the last lecture, and we need to do this because people differ. People produce intrinsically different prosodic cues, and we'd like to be able to do things that are comparable across different speakers. So last time we saw how we could go from the speech signal to a collection of frame-level features, and today we'll move on and look at creating normalized features from those, and from that we can feed into other sorts of feature representations. So one way to motivate this question is to ask, so we've got a pitch measurement, is this pitch high? Well, you really can't answer that question without reference to a speaker's speaking range. So 190 hertz is probably a little low in my pitch range, but for another speaker that could very well be quite a high pitch. So you can't answer this question without understanding the range of the speaker. So we can get a better grip on this by looking at a histogram of the pitch produced by a particular speaker. So here we've got the pitch in log hertz. Pitch is generally log normally distributed. So we'll be using log hertz, and we have a count on the y-axis. And so now you can see the overall distribution of this speaker's pitch, and since it's above sort of the peak there, you would say this is high in the speaker's pitch range. In contrast, if we look at a distribution as in the plot below, you would say that that is probably low in the speaker's pitch range. Now, looking at it like this is all well and good, but that's a visual representation. We'd like to have a quantitative numeric way of describing this high or low. So one way we could do this is by computing a value for that pitch with reference to the speaker's minimum pitch. So we have the speaker's minimum pitch above and in the second plot, and in both cases we could create a representation where the pitch is the observed pitch minus the speaker's pitch minimum. And that would indeed show that the first pitch is higher in the speaker's range than the one in the plot below. The problem here is that extrema, like pitch minima, are very sensitive to different types of noise and distortion. They're sensitive to things like creaky voice in measurement, to background noise, and also to different types of errors in the pitch tracker. And so it's hard to get a really reliable estimate for pitch minimum. An alternative to that might be more robust is using the average pitch. So here we've got the mean pitch for each of our two putative speakers, and so we can compute that value, and now instead of subtracting the observed value, the minimum from the observed value, we can subtract the mean value from the observed value to give us a relative representation of pitch. That's not a bad place to start, but it's got some gaps in that we might have a distribution like this speaker here, but they might also have a much narrower pitch range. And we'd like to have something that captures the difference between the sort of pitch for the speaker in the top graph, where it's a little above their average range, versus the one below, which would be a very substantially higher departure. And we can represent that using something like a standard deviation. So we can compute the mean of the speaker's pitch, take the observed value, subtract off the mean, and divide by the standard deviation. And that is a representation of Z-Normalization, which is a pretty common way of normalizing pitch. Now, there are some limits here. Z-Normalization works pretty well if the distribution is really normally distributed, but as you see from this plot, the speaker's pitch here is not really well normally distributed, and it would be better represented in this case, for example, using, say, 3 Gaussians. Here, probably the lower one is associated with creaky voice, the mid one bimodal voice, and the higher sort of mode there by, say, octaving or doubling errors. And you can formally represent this as a set of tied Gaussian mixtures that you could learn together, and then you could normalize and correct the octaving using that. That's a bit more heavyweight. An alternative is just to use percentiles. Those are quite robust, and then you can represent the pitch value in terms of its percentile whenever you're looking for a feature representation. You might also wonder sort of how much speech do you need to do this normalization? It turns out that based on my co-presenter's previous experiments, you actually don't need that much speech. Maybe 2 seconds or so is pretty good for estimating these sorts of characteristics for a speaker. And that can also be helped by the fact that people tend to start conversations with sort of neutral introductions like, "Hi, how are you doing?" which are pretty representative of the sort of middle of their speaking range. And they might get bored or more excited later on, but that gives you sort of a good reference starting point for computing these sorts of statistics. So we're also interested in features that are not just pitch. So we've looked at extracting loudness, voicing breathiness reduction, and so on. These latter 3, again, you probably want to normalize in some way relative to the speaker. For example, you might have a speaker who is quite breathy intrinsically, and what you're interested in is when they are more or less breathy relative to themselves, and you could use perhaps something like a Z-score normalization. However, loudness is much more problematic in terms of this sort of normalization. So if we ask the same sort of question that we start out with pitch, so we have a value of intensity, is that loud? Well, we can again use a sort of histogram distribution, and intensity can be hard to characterize because there are many, many factors that in the recording setting that affect intensity in addition to whatever the speaker is actually producing. So there's the gain on the microphone's distance from the speaker, the presence of other background noise in the recording area, and so on, all of which make getting a good measure for intensity difficult. In fact, some prosodists just avoid intensity because of these issues, but we'd like to be able to exploit it because it is in fact quite informative, especially in the context of dialogue and turn-taking. So instead, we can use these sorts of distributional measures where for intensity we can observe sort of 2 of these large sort of modes, one which corresponds to silence in terms of the speaker not speaking. That's the lower value, and the higher value that corresponds to sort of their modal speech. And we can represent these again as 2 different Gaussians, and then we can normalize the energy so that the Gaussian centers are at 0 for silence and 1 for speech. Now, the relative distribution of silence and speech is going to vary for somebody's recording based on, for example, how much they're talking, but we can do that sort of normalization and get a reliable representation this way. So in sum, normalization is important for dealing with the variation across speakers and across, for example, recording contexts, but normalization is tricky, and most techniques for normalization are imperfect. So there's quite a bit of work going on disentanglement now to try to develop better representations for things like prosody transfer in things like synthesis. But at the same time, we don't have a perfect representation that allows for sort of speaker-neutral comparisons of prosodic features. And for example, Liz Streiberg has frequently identified normalization as being a crucial component in building a good model for prosody. And many of us who've worked in this field have found that failure to appropriately normalize can contribute to many bugs and also to misleading results and interpretations. So it's important to normalize, but normalize carefully. And now that you've seen these approaches to normalization for frame-based features, we'll continue in the next lecture to look at representations over longer spans of speech that allow us to create more reliable mid-level representations of speech and prosody.